I'll start with measurement error. Do you know what measurement error is? It's the measured value minus the actual or true value. By actual and true value, I mean the same thing, either the actual value or the true value. If we knew the actual true value, then we're done. For example, you're measuring the radius of curvature of a convex spherical surface in problem 1.1. If you knew the actual value of the radius of curvature of the convex spherical surface you're measuring, you could write down the actual value and go home. The problem is that you don't know it. You almost always don't know it. There are exceptions, though. It is known, for example, when it comes to a general constant. For example, the speed of light in a vacuum, the permittivity of a vacuum, the permeability of a vacuum, or the triple point of water. But most of the time it is not known, so then we conventionally replace the actual value with the true value. Since we don't know it, we conventionally replace it with the true value. And conventionally, the true value is a value that is close enough to the true value for a given purpose. In practice, this is most often the arithmetic mean, or the arithmetic mean is also called the mean value. The conventionally true value can also be some table value. And then, when we replace it with the conventionally true value, we get the absolute measurement error from this relationship. Here, x of n means measured value, and x of p means true value, or conventionally true value. This is the absolute measurement error. X stands for some directly measured quantity. If I were to directly measure length, it would be L. If I were to directly measure volume, it would be V instead of X. Then we have a relative measurement error. Do you know what it is? It is the ratio of the absolute measurement error to the conventionally true value. This conventionally true value is most often the arithmetic mean. And the relative measurement error is almost always expressed as a percentage. So you multiply this by 100%. Then we have some reasons why you're measuring inaccurately. And now I will divide these reasons into three large parts: gross errors, also called mistakes, systematic errors, and random errors. Gross errors, also called mistakes, are omitted when processing measurement results. They arise, for example, due to the inattention of the observer or the experimenter, and they can be avoided. This is, for example, when you arrive very tired and the stopwatch shows the number 1.23, and you write down 3.23 instead of 1.23 in your notebook. So, such gross errors are most often noticed when you have several repeated measurements and one value suddenly differs significantly from the others. In that case, you don't consider it. You cross it out and don't take it into account. But you should avoid that because then you have one measurement less. And as I'll explain later, the more partial measurements you take, the more precise the overall measurement. Then we have systematic errors. These are caused by two main causes: the imperfection of the instruments used and the imperfection of the measuring method. Systematic errors lead to values that are either permanently higher or permanently lower than the true value or the conventionally true value. And now we come to the errors of the measuring methods. That's the second group of systematic errors. Errors in measurement methods can be removed or at least eliminated by using more precise methods or by introducing appropriate corrections. So either you use a more precise method when you want to eliminate them, or you introduce a correction that eliminates that inaccurate method. For example, you measure the length of a body at a temperature other than the one you are interested in. For example, you have the task of measuring the length at 20 degrees, and the temperature around you is 35 degrees. Then the method is inaccurate. And then what would you have to do? You would have to subtract the elongation of the ruler due to the increased temperature, but only if you want to be very precise. In your case, you wouldn't do that, because when measuring with the ruler, the error wouldn't be so big that you would have to do that. But I'm saying that as an example.
So, with errors in measurement methods, you also know their sign. For example, you know that your ruler has become longer. Then those errors will be positive.
Then the second kind of systematic errors is the errors of the measuring instruments. They can't be completely eliminated because you have the equipment you have. You could, of course, buy more expensive equipment and bring it to lab exercises, but you will not do that. But even more expensive and more precise equipment are still not completely accurate. So, in any case, you have instruments that are not completely accurate, and you have to deal with the errors of those measuring instruments. It is known only their maximum value, not the sign. For example, if one division of the ruler scale is 1 millimeter, and you measure 4 millimeters with that ruler, then you don't know whether the conventional true value could be as much as 5 millimeters or 3 millimeters. In this case, you don't know whether you have committed a positive or a negative systematic error. A special group of errors of measuring errors is personal errors, or in other words, observational errors, because in this case, the measuring device is your body. For example, let's say you measure with a stopwatch. Then there is your reaction time. So personal errors are errors of your sensory measuring devices, your body, and you don't know their sign. You can't roll them out unless you replace sensory measurement exclusively with instrumental measurement. For example, if you measure time with a stopwatch, due to the imperfection of your vision and nervous system, or I would say due to not having a completely perfect vision and nervous system, you're going to press that stopwatch button a little bit later than you should, so there's some delay. That will be in task 4. If you wanted to avoid this, you would have to replace it with a purely instrumental measurement. For example, there would be a sensor that would start the timer in the computer, and then another sensor which would stop the time in the computer. For example, if a ball falls, at one moment the sensor would start the time, and at the next time another sensor would stop the time. Nevertheless, sometimes you have to measure using your own body, and therefore you have to take into account personal and observational errors. For example, in task 4, you'll just have a stopwatch and therefore also personal and observational errors. Then we have random errors. That's the third important group of errors. Their origin lies in the unknown and random causes, such as the probabilistic character of the measured quantity. This is the case, for example, if you were to measure the density of this air around you. There are some density fluctuations because the particles are moving erratically and there are eddies and flows, so there are density fluctuations. Another example is the uncertainty principle. If you wanted to measure the position of a particle very precisely, you would encounter the uncertainty principle. There will always be some random error. We do not know the size of these errors. They are irremovable. We determine their size by mathematical statistics, and we can at least eliminate them. The more measurements we take, the more we can eliminate them. Then there's the important concept of normal distribution of random errors. It is the Laplace Gaussian distribution, the Gaussian curve. Do you know the Gaussian curve? Let me demonstrate. This x is a randomly measured value of some measured quantity. And this random variable has a mean value. Random error is measured value of x minus the mean value me, and you will almost always measure random values of measured quantities roughly in this distribution. Most often, you will measure some value that is close to the mean value, but sometimes in one or two measurements, the measured values can be significantly different from the mean value. There is an important term, the standard deviation. It's precisely because of that standard deviation that I'm drawing this distribution for you here. The following applies. The probability that with a normal error distribution, you will measure a value in this interval, around the mean, is approximately 68.5%. And the probability that you will measure a value within the interval μ plus or minus 2 sigma is already about 95.5%. We'll use that a little later. But now let's get to the basic calculations you'll be doing. For example, you will be calculating the arithmetic mean of the measured values. Do you know how to calculate the arithmetic mean? This is the arithmetic mean of n measured values. It is also called the sample mean of n measurement results. The word sample is used because you have a subset, a sample taken from all possible measurement outcomes. You only have n measurements, so just a sample, and from that sample you calculate the mean. It is therefore the most probable value of the measured quantity, and if you were to measure an infinite number of times, it would converge to the true value. Why am I writing this to you here? Because your goal in the laboratory exercises will be to write the measurement results in this form. For example, in the first task, you will write the result that the radius of curvature is equal to some most probable value, plus minus deviation. This is the standard uncertainty, the combined standard uncertainty. I'll write how to calculate it in a moment, but the C stands for combination, and the R is there because it's a quantity called R, and that's our goal. So we need to calculate the most likely value and the combined standard uncertainty. This is the absolute combined standard uncertainty. This is the relative combined standard uncertainty. The R in front of the C stands for relative. We showed the calculation of the arithmetic mean, and now let's show how we're going to calculate the uncertainty. But we'll get to that a little later. Before that, I am going to write down what the deviation of the ith measurement is, because you'll be writing down the deviations in your measurement tables. The deviation of the ith measurement is the ith measured value xi, minus the arithmetic mean of the measured values of the quantity x. Then there's another term, the sample standard deviation of the arithmetic mean. I denote it as S x with a line. We use it because the arithmetic mean is just an estimate of the true value. So even with the arithmetic mean, we determine its deviation. Next, we'll show that this is actually a standard uncertainty of type A. Okay, now let us speak about the concept of measurement uncertainty. A deviation is a single value. A measurement error is also a single value, but the uncertainty of a measurement result is the interval of values within which, with a certain pre-selected probability, the true value of the measured quantity lies. Why with a pre-selected probability? Because here I had plus minus twice combined uncertainty, and when there is double combined uncertainty, then there is a probability approximately 95.45% that the true value lies within that interval that I wrote here. So we choose the probability that the true value lies within the given interval. According to the chosen probability, we determine the coefficient by which the absolute combined standard uncertainty is multiplied. If we multiply the final absolute combined standard uncertainty by a larger factor, for example by 2 or 3, we get a greater probability that the true value lies in that interval than with a factor of, for example, 1. So since I had it here before that r equals the arithmetic mean plus minus UCR, I actually wrote an interval of values, because r plus minus 2 UCR is an interval of values. Let me write that again. Then the true value of r lies in that interval with a probability of approximately 95.45%. And if we were to expand it so that there is 3 times the combined uncertainty, then we have a larger interval and a greater probability that the true value lies within that larger interval. Now we're going to divide it up. The quantities that you're going to measure are either directly measured quantities or indirectly measured quantities. Directly measured quantities are those that you measure directly. For example, you would measure length with a ruler from one place to another. In such a case, you are measuring directly. The length would then be a directly measured quantity. And for directly measured quantities, you will always calculate the standard uncertainty of type A and the standard uncertainty of type B. And then you combine them into a combined standard uncertainty. Does anyone know how to calculate the standard uncertainty of type A? I denote it as UA. I am putting x here because it's for the quantity x. The standard uncertainty of type A is obtained by statistical methods from measured data. Its value decreases with the increase in the number of repetitions of the measurement. Its causes are random phenomena, for example, natural fluctuations of the measured quantity. We calculate it from repeated independent measurements of the quantity under the same ambient conditions. That under the same ambient conditions is quite important, because if you have to make 10 measurements, you don't divide it up so that you make 5 measurements one week and 5 measurements of the same quantity the second week, because in the second week there would be different conditions. So you must repeat the measurements, if possible, under the same conditions. And that's why you should take all measurements of one quantity, if possible, one by one. How is the standard uncertainty of type A calculated? It is actually the sample standard deviation of the arithmetic mean. It should be calculated for at least 10 measurements. If you take fewer than 10 measurements, you should make corrections or use another method. Then we have the standard uncertainty of type B. It is obtained in a different way than the standard uncertainty of type A. Its value does not depend on the number of repeated measurements. Its cause is known or identifiable sources. For example, the imperfection of the used measuring instruments, their limited accuracy, and imperfection of the used measurement method. So the uncertainty of type B relates to systematic errors, and the uncertainty of type A relates to random errors. The uncertainty of type B is calculated like this. X max is the maximum permissible measurement deviation that is unlikely to be exceeded. The word unlikely means, for example, with a probability of less than 5%. X max is often determined as the smallest division of the measuring device. For example, for a millimeter ruler, it is 1 millimeter. Or it is determined as the maximum permissible error calculated from the accuracy class of the measuring device. This accuracy class is usually given for electrical measuring instruments. For example, if you have a digital multimeter, it has an accuracy class. If you are measuring, for example, electrical voltage, then U max would be, for example, 0.2% of the maximum range of the voltmeter, plus minus the last two digits. And do you know why the square root of 3 is there? In high school, they get around this by telling you to divide the smallest division of the scale by 2, and then it's roughly the same as dividing it by the square root of 3. But this is more accurate. The square root of 3 is the factor for the uniform distribution of errors. For example, you can have this interval for measuring a length with a ruler. As I said before, if you measure 4 millimeters, the real value could be as high as 5 millimeters or as low as 3 millimeters. However, if you assume a uniform distribution of error, which you will usually assume, then the true value is equally likely to be anywhere in that interval. This situation is represented by the factor of the square root of 3. In special cases, when you have good reason to believe that the true value is more likely to be in this part of the interval than in this part, you would not follow the uniform distribution, and the factor in the denominator would be different, but I think you will almost always use this factor. If you get the standard uncertainty of type A and type B, then for the directly measured quantity, you just combine them into the absolute combined standard uncertainty, UCX. UAX and UBX should always be independent. In practice, you will almost always have this condition approximately fulfilled. And as I mentioned in this entry, if you have a combined standard uncertainty, you have a confidence level of approximately 68.27% that the true value of x lies within this interval. And if you multiply your calculated absolute combined standard uncertainty by 2, you have a level of confidence of about 95.45% that the true value of x lies in this interval. Multiplication by 2 is probably the most commonly used. You could theoretically multiply it by 3 instead of 2, then you would get a level of confidence of about 99.7% that the true value of x lies in that interval. But you will be fine with factor 2 because it determines a good enough certainty. Then we have the relative combined standard uncertainty, URCX. It is most often expressed in percentages. Important note, write the numerical value of this absolute combined standard uncertainty with two significant figures. Do you know how to count the significant figures in a numerical result? For example, on a calculator, you would get this absolute combined standard uncertainty of the quantity x, 0.00234. How many significant figures does this number have? We count the significant figures from the left, from the first non-zero digit to the right. So how many significant figures does this number have? Tell me. We'll find the first zero digit from the left. The first non-zero digit is the digit 2, and we count to the right. First, second, third. It has 3 significant figures, and we write standard uncertainties to 2 significant digits. So you round it to the number 0.0023. With a direct measurement, you should be done with this, because in that case, you can write the result in this way. But sometimes you have an indirect measurement. For example, density is calculated as mass divided by volume. Suppose you didn't have a hydrometer and could only directly measure the mass and volume. Then the mass and volume would be directly measured quantities, and the calculated density would be an indirectly measured quantity. With the indirectly measured quantity, let's call it y, there's a certain relationship there. It contains directly measured quantities. Let's say it depends on m directly measured quantities. For example, you can imagine that x1 is the mass, x2 is the volume, and the y would be the density. Now again, you need to calculate the arithmetic mean and the combined standard uncertainty for this indirectly measured quantity y. That's your task. So what are you going to do? You have 2 options for the arithmetic mean. Either you add the arithmetic means of the mass and the volume to the relation, for example, for the density, and from that you calculate the arithmetic mean of the quantity y. Or you calculate the density for the individual measurements. Let's say for m1, v1, you calculate rho 1, for m2, v2, you calculate rho 2, then you calculate rho 3, rho 4, etc., and then from that you calculate the arithmetic mean y. Either approach gives the same value in almost all cases, so you have a choice here. I recommend the first approach to you. To calculate the arithmetic mean of the indirectly measured quantity, you substitute the arithmetic means of the directly measured quantities into the equation for the indirectly measured quantity. The combined standard uncertainty can be calculated using Gauss's law for the propagation of uncertainty. This is all under the square root. This is Gauss's law of propagation of uncertainty. And now quickly, let's show an example for problem 1.1. That is for the measurement of the radius of curvature of a portion of a spherical surface using a spherometer. In that problem, you have this relation for the radius of curvature. H0, H1, and the small a are directly measured quantities. For these, you'll calculate the standard uncertainties of type A, type B, and the combined standard uncertainty. And the R is an indirectly measured quantity. So you can simply calculate the arithmetic mean of the radius R by substituting the arithmetic means. And the combined standard uncertainty UCR I could have just substituted the expression h0 minus h1 for h, but it's probably clearer this way. But if I leave h in the relation for the absolute combined standard uncertainty, I have to calculate it for h separately, because h is also an indirectly measured quantity, and it is calculated using h1 and h0. The partial derivative comes out to 1 here and minus 1 here, so it's simple. What exactly is it that you don't know about this relationship if you want to substitute it in? Calculating arithmetic means is easy, but you also need to calculate UCH1, UCH0, and UCA. A is now a directly measured quantity. So here we calculate as before, the absolute standard uncertainty of type A and the absolute standard uncertainty of type B.
If this video helped you, give it a like.